lately there is more and more interest on 3D printing of smart material to create the final product, the final design of a product which has not only the geometry, the strength, but also the smartness.
Excellence at Work is sponsored by Youngstown State University.
You were part of the effort, part of the team that wrote an article in Microscopy and Analysis magazine. I'm not going to try and say the name of the article that you wrote. You can say that, but could you go ahead and tell us a little bit about the article and what it was about?
Yes, thank you, Mike. Yes, so the article is titled Modeling and Characterization of Binder Jet 3D Printing Nickel Manganese Gallium Components using X-ray microscopy. It was published in the Journal of Microscopy and Microanalysis. It's one of the journals of Microscopy Society of America, which is the largest gathering of people with interest in microscopy. And it was published last year in August. This work was done with a few collaborators. So we have two graduate students involved in the project, Stefan Isako and Christopher Banzar. The other author is Matthew Caputo. He's a former YSU student. He's currently a faculty at the Penn State Shenango. And also we have Bart Winiarski. He was the person from one of the companies that provided the instrumentation for this article. So basically what we did in this article, we tried to continue a research project we started 8 years ago on 4D printing of nickel manganese gallium. So this was original attempt we did to combine 3D printing with the smart materials, shape memory alloys. And in this case, the shape memory alloy that we used was a magnetic shape memory alloy made of nickel, manganese, and gallium. We started the project by taking advantage of the opportunities that we have here at YSU on the 3D printing. As we know that the time that America Makes was created here in Youngstown, YSU got heavily involved with the 3D printing. And I tried to bring this advanced manufacturing technique into our research. And since I was familiar with the shape memory alloys, I thought a good opportunity to combine the smart material, which is a shape memory alloy, with advanced technique, manufacturing technique of 3D printing. So basically, what we did, we printed the material, the shape memory alloy, and after that, we functionalized them. So we made the material to have a fourth characteristic, and that was the change shape as a function of external stimulus. So basically, our 3D printed material, not only that has the mechanical strength that it's supposed to have while used in different applications, but also we took advantage of the smartness, the functionality of that material.
I'm going to have you go back for just a minute. I'm pretty familiar with additive manufacturing. I've spoken to many people and we've done many stories on it. I am not familiar with shape memory alloy. So I guess could you go back and talk a little bit about what shape memory alloy is and how you're using it, and I guess how that material, what the benefits or what the differences are using that material in additive manufacturing?
Yes, absolutely. So shape memory alloy, it's a smart material. It's a material of the future. What makes this metallic material smart is the fact that it can change shape between two defined geometry when an external stimulus is applied. And this geometry can shift between one low temperature geometry and another high temperature geometry when the temperature is changed, or in the case of our materials, on the magnetic field is applied. So basically, we can shift shapes by simply applying temperature or magnetic field. And what are the advantages of such a material for engineering application? There are many, many advantages because one of the application of shape memory alloy, it's in the actuators. What is the actuators? So the actuators, it's a electromechanical system which moves stuffs. Like, for instance, we want to deploy an antenna, or we want to open a door automatically, We want the wipers on the windshield to move. In that case, what we have, generally, we have a power source, we have a motor, and we have a mechanical system, a gearbox, for instance, to do this. And that takes power, components, and volume to have this. What a shape memory alloy can do, we can reduce the volume of that system, make a small, very compact system, which performs exactly the same function. And that's the functionality, that's the application, the applicability of the shape memory alloy, is that we replace a complex device with a much simple device, with a piece of metal practically, which can perform the same action, but the lesser energy consumption, compact in the compact mode, and eventually much cheaper to produce it.
So you mentioned windshield wipers. I'm trying to visualize what you're saying. I understand what you're saying. I'm trying to visualize it, I guess, in that application. How could that be used with windshield wipers? Because that's something we see every day.
Yeah, so basically what we have in the windshield wiper mechanism, we have a motor and we have a few levers which moves the wiper across the windshield. Instead, what we can do, instead of having a motor and the mechanism, we can have a simple piece of metal connected to the wiper. And by applying an electric field or by applying a magnetic field, that wiper is going to move by the metal bending back and forth and moving the wiper across the window. So instead of having that complex mechanism and quite a lot of power consumption, we can have a piece of metal that bends and moves the wiper across the windshield.
Are these alloys expensive? Are they readily available? Are there enough of them for this type of production?
Yes and no. So the answer is both. Some of the alloys, for instance, the most popular shape memory alloy are nickel titanium, so a combination of nickel and titanium. This is readily available and it has a lot of application. It's a multi-billion dollar business in medical field, aerospace industry, and automotive industry. So nickel titanium, the technology for nickel titanium for this thermal activated shape memory alloy, it's readily available. The materials are quite are available and they are quite cheap to purchase. They on the other hand, the material that we use in our application, which is a magnetic shape memory alloy, nickel manganese gallium, it's not available. It's under development.
So what is your research? What have you found doing your research?
So basically, what we try to do, we are trying to improve this nickel manganese gallium material. So the way that we try to take advantage of the capabilities offered by additive manufacturing technique, the 3D printing. So one major problem with nickel manganese gallium is that we cannot machine it. This material is brittle. It's like a glass. Actually, it's a metal, but it behaves like a glass. It's very brittle. We can, like in the glass, we cannot drill a hole using a drill bit. The same with nickel manganese gallium cannot be processed by machining. So what additive manufacturing does, it gives us a near net shape just by printing the material. We don't need to machine. We can create the part directly by printing. And we take advantage of that to prove that parts made of nickel manganese gallium can be 3D printed. And not only that can be 3D printed, that they can behave the shape memory effect. And what we call this behavior, we call a 4D printing, because we have a 3D printing manufacturing plus the shape memory effect added on top of that, and that's the buzzword of 4D printing, which it's of interest. Actually, as I say, we start working on this 8 years ago, and lately there is more and more interest on 3D printing of smart material to create the final product, the final design of a product which has not only the geometry, the strength, but also the smartness to do stuff, to do same things.
So this substance is so brittle you can't machine it, but it will bend if you give it the right stimuli.
It will bend to a certain extent. It's still, we didn't solve the brittleness problem, but at least we proved that we can achieve complex geometry by 3D printing. and it can have some mechanical, it can take some mechanical load, and also can have the functionality that we needed for different applications. No, it's still a long way, I suppose, to improve this material, but at least this is a one small step in the right direction.
Okay, very good. Are you talking with any businesses or any companies around here, or any industries who are interested in this technology or see a use for it in their processes?
We are in touch with many companies. It's part of my job to be in touch with the local companies. What we try to collaborate with NASA Glenn to follow their step in this direction, because for the other material that I mentioned, which is commercially available, nickel titanium based alloy, they are at the top. So they do the top level research in the development of shape memory alloys for space application. And we're trying to keep in touch with them. We are trying to learn from them. And eventually, if the opportunity arises to implement our material in some industrial engineering applications.
This just really goes to show, I mean, you're talking about 8 years ago. That doesn't seem that long ago. I can remember when America Makes came around here, and we were all trying to catch up and learn what additive manufacturing was. And, you just 3D print something, and it seems like every couple of months there's a new type of additive manufacturing or a new material, or they're using pellets, they're using liquids, they're using just so many different applications and processes and uses for additive manufacturing that I think we're just now starting to get our heads around.
Yes, I'll say I know it was overwhelming for people outside the field, but it's even overwhelming for us in the field, because the field is very dynamic. New technology are coming, new materials are coming. The approach, the mindset that we need to have in order to create engineering application using parts made by additive manufacturing, it's different. So the conventional approach of material processing and material properties that we have using, like, let's say, machining or casting technology or powder metallurgy, it doesn't necessarily apply to the materials 3D printed. And we are still learning. We are still at the beginning of the application of 3D printing in the engineering field. It's still, we are advancing every year, every day, every hour. There are news coming out from people improving the technology, improving the materials, new material for 3D printing. It's there. And I think we still have a long way to go until that will reach the full level of implementation in engineering the same way that we have with the conventional technology.
Excellence at Work is sponsored by Youngstown State University.